So welcome everyone. In today's session we talk about the sources that are used for making any medical optics system. When it comes to sources, one of the basic or most utilized source that you will find in any medical optics device such as pulse oximeter is a light emitting diode. So let us try to understand how does a light emitting diode works. Okay, so as you can see, the first discovery of light emitting diode was well early in 1907, and you can see over here what he has mentioned on applying a potential of 10 volts between 2 points in crystal of carbonum, the crystal gave out a yellowish light. Okay, so there are two important points. The first point is the application of voltage, a certain voltage, and the second point is the material. While we talk about the source, the material is one of the most important part. Which material that we used, why we use it. So we will try to learn about the different materials that is used to make a light emitting diode and how much voltage you need to apply and why a yellowish color, like why not a red color, why not a green color. So we will try to understand the working principle of it. So once we apply a 10 volt to a material, it gives you red color. I apply the same 10 volts to another material, but it gives a yellow color, right? So why is that difference? So we'll try to understand the same. So this was by H.J. Round, the work that was given in 1907. So a light emitting diode is nothing but a PN junction diode. So I am sure well sure that you will know what is actually a PN junction diode. It's intrinsic material. While we dope it one side with more p-type dopants, while the other side we dope it with n-type dopants, and we just make them together to make it a p-n junction diode. Okay, one more important thing that comes into the mind is a spontaneous emission. So light emitting diode works on the basis of spontaneous emission. Now what do we mean by spontaneous emission is that we cannot control how the light is being emitted, or in other words the photons being emitted. The photons will be emitted now, it will be emitted after some time in order of some nanosecond interval. So they are not emitted or generated at a single go, okay, at a single instant, for example. Okay, they are emitted with some time difference. This time difference of course is in order of picoseconds, nanoseconds, so it's not in our control. Okay, so that's what is mean by spontaneous. It's a kind of a probabilistic emission. Okay, and another part is that the amount of light, the quanta of light that is being generated is proportional to the band gap of the semiconductor. So we'll learn about that, what do you mean by the band gap and what is the quanta of light. So if you see the light emitting diode, you can see over here that it combines it actually has two wires coming out of the light emitting diode. One is the long one, other is the short one. The long one is actually the anode, and the short one, the length whose wire is short, or the lead which is having a smaller dimension or smaller length, is actually a cathode. Okay, both the legs actually combine together through a wire bond. You can see over here, this is the wire bond, and this is the LED die, okay, or a semiconductor p-n junction die, and this is the one which is actually emitting the light. The wire over here is kept for the conduction of electrons, and the wire over here as well is for conduction of electrons, and it is encapsulated by an epoxy, and this epoxy is just to safeguard the semiconductor die, so that there is no harm because of the external rise in temperature, or it could be because of the flow, or it is because of flow of air, or it could be because of moisture. So it doesn't harm the working of the semiconductor die. That's why there is an epoxy layer on top of it. This epoxy layer is also interesting because based upon this epoxy layer, the light could also be tuned in a particular direction. We can reduce its cone angle or increase its cone angle, make it very narrow as well as wider based on the radius of curvature of the top epoxy layer. Okay. The good part of the LED of course is that it can work for a very long period of time. It is efficient as compared to the tungsten or halogen lamps. Intensity is also in our control. It is cost effective and it's kind of very robust. We can use it in any way that we want. Okay, so you can see this video, and you can see the how. So this is the semiconductor die that I was talking about, and the current is being passed to this, and you can see that it's becoming light is coming out of this semiconductor die. Okay, so I'm just giving it the current, and it's coming out. It's becoming more brighter, and after some time I'm switching off the current supply. Right, so you can see that it's not anymore emitting. Okay, so this is what is the same thing that I showed in the previous slide. I'm just showing it actual working condition of that. Okay, so how does a light emitting diode work? As I said, it is about two intrinsic semiconductor material. On the left hand side, I dope it with p-type dopants. On the right hand side, I dope it with the n-type dopant, so it becomes p-type and an n-type. And once I join them together, you actually get a junction. Okay, and through the junction, when I actually apply a battery or a potential difference across this p and n type semiconductor material, there would be the electron and the hole would be actually crossing over, and there would be a the electrons will try to fill the holes. Okay, and once it tries to fill the hole, which is also known as a recombination, right, and that will actually emit a single photon. So here you can actually see the electron is kind of moving towards the left hand side and the holes are moving towards the right hand side, and what you can see is a spontaneous emission. Here you can appreciate with this animation what is a spontaneous emission. So here you can see the light are not generated at a single go. You can see that this photon is being generated now, then over here, and then over here, and over here. So then once it starts to emit at a spontaneous kind of a spontaneous emission or kind of probabilistic emission, the next thing is to just capture the light photon and then just move it in a certain direction. Okay. So this is how a semiconductor light emitting diode actually works. It's just based on the recombination of the electron holes and electron pairs. Okay, it's very much similar to a Mario game that you would have already played. You can see over here the Mario is actually coming over here and then just jumps on a question mark, and then there is one kind of cake which is coming out over here. So very similar to this, you have the electron which are moving from a conduction band to a valence band, and because of that jump, so the holes are over here and the electrons are over here. So once we apply the electric potential, the gap between this actually reduces, the band gap reduces, and then the electron can jump from a higher state to a lower ground state, which actually emits a photon of a particular energy. Okay, so here you can see now I have applied the voltage, so this gap has now significantly reduced, and then it actually the electrons can actually travel to this side, and these electrons can actually move down over here, and it can actually give you a photon of a particular energy, and the energy of the photon is equivalent to the multiplication or the power of multiplication of Planck's constants into the speed of the light. Right. So here, this is the speed of the photon. So let us see, go forward and try to understand what is happening. And here you can see the electron is now at conduction band, and the hole is in the valence band. Now once I apply the potential, you can see that it actually comes down and it actually emits the photon. Okay, and you can see that so the band gap, so this is the difference of energy over here, and this difference of energy is also known as EC minus EV, which is equal to EG, and that is known as the band gap over here, and that is equivalent to HC by lambda. Okay, this is also equal to h nu, and actually h is the frequency. Apologies, it was not this. So here h nu band gap is equal to h nu. So this h nu, h is the Planck's constant and nu is the frequency. Okay, yeah. So the frequency also is equal to speed of the light over the wavelength, operating wavelength. Okay, so you can see that it is hc by lambda. Okay, so the emission wavelength. So what is the emission wavelength? So emission wavelength depends on the band gap. So lower the energy, the band gap, higher the wavelength, because your energy is inversely proportional to the wavelength. Okay, so for example, as you can see over here, I tried to calculate over here. So I've given one of the example. For example, I'm using gallium arsenide. It has a band gap of 1.43 eV. Now again, what do you mean by band gap? Band gap means you have the conduction band and you have the valence band, and your electron is placed in the top and your hole is present in the bottom, that is in the valence band. You have electron in the conduction band. Okay, so your electron, so this is your EC, this is your EV, right? So your EG is nothing but equal to EC minus EV. Okay, so we try to understand if we have the difference between the valence band, energy of the valence band, conduction band and the valence band equal to 1.43. What is the light going to emit? So if the electron moves from the top to bottom and it actually emits one photon, what is the wavelength of the light, right? So we try to understand that. So that could be understood if we know what is the energy. Now we know what is Eg, that is 1.43. We just need to plug in to the actual equation. You can just do it easily. E equal to lambda h hc by Eg. Okay, so your energy is equal to hc by lambda, right? So if you just plug in place all these values into this, you can actually get what is the wavelength. Okay, operating wavelength. So for example, you have all the colors. You have violet, blue, green, yellow, orange and red. Now what is it corresponding? So we have already told about that each of these wavelength, each of these colors have its corresponding wavelength. Now we will try to understand, does this each of these wavelength corresponds to any other parameters like energy, right? So for example, violet not only is understood by 300 nanometers, but it is also understood by 1.3 or 3.17 eV. Okay, you can tell the green is given by wavelength of 540 nanometers, but at the same time I can also say that the green light is having an energy of 2.52 eV. Similarly, the red light, I can say that it is having a wavelength of 630 nanometers, 650 nanometers, but it could also, I can also say that the red light has energy of 1.62 eV. Both are interchangeable. We can use either eV or wavelength. Okay. Now, trying to understand when do we actually get the emission? This is not always the case that we get emission. It is only the case where we have direct band gap. On the left hand side, you can see that it is a case of conduction band and valence band. The peaks and the trough actually match each other on the same axis. Okay, so this is a case of direct band gap. Okay, this case of direct band gap. So here the peak and the trough matches each other in the same axis. Okay, at the same momentum. So this is known as, this kind of materials are known as direct band gap. However, in other cases, you can see that the trough of the conduction band and the peak of the valence band do not actually match with each other. Okay, so there is a case where this is the kind of material which are indirect band gap. So there are a lot of losses in such kind of materials, and it kind of doesn't give much effective light sources in such kind of materials cases. Okay. So let us see the different kinds of materials which are direct and indirect band gap. So you can see this is silicon, gallium arsenide, germanium, indium arsenide. Okay, so these are the different kinds of materials and their energy band diagrams, and from there you can actually see for the silicon it is having significantly different, so that is a indirect band gap. For otherwise, or for all the others it is actually a direct band gap, and that's why silicon, if you is actually has a lot of losses if you can want to shine the light using a silicon material. But on the other side, silicon is used for as a detector material. You can actually use as detecting. That's what we talk about when we talk about optical detectors. Okay. While gallium arsenide and indium arsenide are actually used for emitting light using LEDs for LEDs. Okay, so let us see for all the materials. So this is a table where all the materials have been mentioned, and most important is the Eg on the left hand side. Okay, so this is the band gap between, that is the energy between the valence band and the conduction band. For example, you have gallium nitride which comes around 3.5 eV. So this 3.5 eV means it corresponds to very high energy, and this high energy means it could be able to, with gallium nitride material you would be able to emit blue light or violet light on similar range, right. Now if you see this ALP, that is aluminum phosphide, it is having energy of 2.5. So it means that you would be able, using aluminum phosphide, you would be able to emit green light. Okay. Then you have gallium arsenide. So gallium arsenide is coming up energy of around 1.5. So with gallium arsenide or indium phosphide, you would be able to emit lights in order of red on those regions. If you go even lower, indium selenide and indium arsenide, it's around 0.5 eV, means you can go into NIR range of light source using NIR band 1 or band 2 energy light source. You can use those things as well. Okay, so based on the material, we actually can choose which light we want to emit. So that is very important to know. So this is a kind of a research in the material itself. So a lot of research is happening on the materials, which materials to use to emit a particular light in the field of optoelectronic research. Okay, so this is how the fabrication of typical LED looks like. You have so it's not just adjacent p-type dopant semiconductor on the right hand side, n-type semiconductor, but it's actually arranged in this format over here. So you have the substrate, this is for giving the rigidity, and then you have n-type dopants over here, and then you have p-type over here, and then the recombination happens in the channel somewhere. Okay, and then the light is given out over here. This is how the bonding has been taken place, the wire bonding, and here we give positive and then negative, right. So so this is how the electrical contacts actually happens. Okay, so I think this one is the negative part. Yeah. Okay, so this is the positive and this is the negative part over here. Okay, so that's how it actually happens. How does the light emitting diode works? Okay, so in the next session we will talk about how the laser actually works and how laser is quite different as compared to the light emitting diode. As we discussed, light emitting diode is a spontaneous emission, but when we talk about laser, we will see that laser is a stimulated emission, which means that we can control when the photons are being generated. We can control in such a fashion that all the photons are being generated in a single time, instantaneously together, and then again its multiplication can happen again at a single time, and all of them will happen at the same time. And that is why the intensity of the laser becomes very high. It also has high coherence. We can pump a lot of energy at a single instant of time, and that's why laser has been coming up as one of the most important sources in the field of medical optics. Thank you.